Hey there, chemistry team. It's your chemistry coach coming at you with my periodic table shirt with the acid holes in it. Woo woo! Or as my daughter would say, I wear this shirt periodically. Okay, anyway, we're going to do a topic today that kind of transcends several of the chapters that we have that involve equilibria. Some general actually quite a few general chemistry courses I've taught. I don't even talk about this particular concept, but we have a few labs that are actually going to measure this effect called the salt effect and how it impacts equilibrium constant values. Because the question is, are equilibrium constants truly constant? Oh, we haven't looked at things like temperature effects, or what if I'm looking at the solubility of a slightly soluble solid in pure water versus in a sodium nitrate solution, or if I'm looking at a weak acid or weak base ionization in pure water versus what if that is in potassium bromide solution. Does the presence of those other ions somehow impact the equilibrium and cause the equilibrium constant to change? Turns out, yes, otherwise why would I be doing this video? So let's introduce the salt effect. What it is, I want you to be able to conceptually see this, and then we will quantitatively look at how it impacts equilibrium constants, and it might blow your mind a little bit here. So salts obviously are soluble ionic compounds, so forming electrolytes. So electrolytes are any charged species. So gobbling down your Gatorade, you're getting sodium ions, potassium ions, chloride ions, those kinds of things. So whenever we say electrolyte, just think charged species or ions in solution. But I want to look at this from a molecular perspective. So in two scenarios, let's look at, say, hydrofluoric acid, a weak acid, ionizing in water. Let's do it in pure water. And then let's look at it in a second scenario where it's in a pretty dilute potassium bromide solution. What's the difference? Let's focus on pure water first. And that's what this AQ stands for. Aqueous means it's dissolved in water. Lots of water. But remember, water's slightly polar. So what I'm going to do is I'm going to erase the AQ here. Let's erase that AQ and show you what is actually happening here. So if I look in solution, that fluoride has a negative charge, -1 charge. The hydronium has a +1 charge after the ionization, right? But if I'm in pure water, water's polar, right? The oxygen side is partially negative. The hydrogens are partially positive. So don't you think a certain end of the water would be attracted to the negative fluoride? The hydrogen side. And for water, the oxygen side's attracted to this. So what this means, the AQ means these are surrounded by these water molecules that have these partial charges, right? So if I put those lone pairs there, so water has a partial negative and a partial positive. So you get this kind of an ion dipole attraction. Remember, we talked about intermolecular forces in an earlier chapter. So water molecules are going to surround this species in a fashion like that. I could keep drawing them over and over, but imagine a shell of these forming around it. Get the basic idea? It gets a little crazy. I won't do it in the center, but imagine a sphere of these water molecules surrounding that hydronium ion, right? That's that shell, right? It's been solvated. That's what the AQ stands for. Because we don't want to draw this all the damn time, right? So we just write AQ and go, that's what that means, AQ. Same thing for the fluoride, but flip these around. It's the hydrogens that are attracted to it. So you get the hydrogens with our partial positive, you get the water with the partial negative there. And so this is going to surround the fluorides like that. So you get the partial positive, partial negative, get another one like that, and on we go. So you also get a sphere of water molecules surrounding that fluoride ion. That's what the AQ is. Now let's look at the same scenario. But what if we have the presence of some potassium ions? We've dissolved another salt in there. How does that impact this equilibrium, right? Because obviously this donates its H plus over. That donates its H plus, forming the conjugate base and the weak acid. But those can recombine. They're moving around in solution. There's not a lot of them, but they might recombine. This, not combine, and this could donate its H plus over and go back this way. That's why you have this equilibrium of constant rates. Well, what's going on here? Let's do the same thing over here. All right, I'll use black this time. We got the hydronium, we've got the fluoride, so we're still going to have some water. All right, so I'll draw a couple water molecules, for example, here. You're still going to have lots of water floating around. Lots of water floating around. Here and here, you get the partial negative. But we're also going to have potassium ions and bromide ions. Potassium ions are positive. Bromide ions are negative. They're going to be moving around. They're not part of the equilibrium system. They're not involved in this reaction at all. But don't you think these positive hydronium ions, they're going to probably repel, kind of be repulsive towards the positive potassium, but slightly attracted to the bromide ions? So let me do the bromide ions in blue here. Aren't you going to effectively see some bromide ions getting around and surrounding that hydronium ion? Right? They're electrostatically attracted to it. It's not going to form a reaction, but it gets around there. And the same with the fluoride. We still have the water molecules. Right? There's still a bunch of water molecules attracted to it. So I'll draw a couple more water molecules here. Getting the idea. Lots of partial charges here. So still got that sphere, but that's a negative charge. It's going to be slightly repulsive towards the bromide ions, but slightly attractive to the potassium ions. So if we take some potassium ions, you're going to see these potassium ions kind of surrounding it. You get this shell. These are inter-ionic forces, summed up in the salt effect. How does that affect equilibrium? This is going to be key. Remember, we are ionizing going this direction and ionizing back this direction. They've got to get close enough for this species to donate its H plus back, right? And in this scenario, there's nothing really blocking their way, just the water spheres. But here, do you see that? You've got some bromide ions in the way, some potassium ions in the way. It's like trying to go give somebody a hug, and then, I go to give my wife a hug, and then my son gets in the way. It's like, oh, I want to get in there. So I go to give my wife a hug, and my little son squirts his way in the middle. It's harder to hug my wife. So this becomes more difficult, and it's harder to go back this direction. Right? It's harder to go back the other way. So effectively, the presence of these other ions, the salt effect, it's effectively reducing the concentrations of those species. Makes it harder to ionize. So I'll leave this here. So it's effectively reduces concentrations. Decreases concentrations of the ions. That's what the salt effect does. Now, ponder that from a Le Chatelier's principle perspective. Ooh, if the presence of the potassium bromide, this is totally non-reactive salt, the presence of those ions effectively reduces these concentrations, right? Those are effectively reducing. Well, what happens when you disturb an equilibrium by reducing the concentration of something? It shifts towards it in response, doesn't it? So what's going to happen if you add the presence of this inert salt? It's going to shift to the right, isn't it? And it's going to increase the ionization of the acid. Oh, let's look at that for a weak acid, weak base, and a solid. Let's take a look at this effect of the salt effect qualitatively, then we'll do it quantitatively. All right, I wrote up a new board to try to put in words what I was talking about pictorially in the last one. All right? So if you've got an inert salt, and this is something you add, so we've got an equilibrium system, weak acid, weak base, slightly soluble solid, in equilibrium. And normally we just treat that as in water, right? But what if we sprinkle in some inert soluble salt? Inert meaning it's not reactive, it's not part of the equilibrium expression or anything like that, but the presence of those cations and anions can distort the equilibrium. So the ions from that inert salt make it more difficult for the ions in the equilibrium, right, like we showed on the last page, from recombining or interacting with each other, creating an effectively reduced concentration. So if I have potassium ions, they're going to surround this hydroxide or surround this sulfide. Here's examples. This would be like methylamine ionizing as a weak base in water to form the methylammonium ion in hydroxide, or silver sulfide solid in equilibrium with its ions in solution, the two silver ions and the sulfide ion. If I put potassium bromide or something like that in there, potassium ions would surround this, surround that, and then the bromide ions would surround this and this, effectively masking them from each other to a small extent, making it harder to go back the other direction. The net effect is it effectively reduces their concentration, which causes the equations to shift to the right. So that's going to make this weak base ionize more, so the percent ionization would go up. It would change the pH from what you would imagine. So these would be different than what you would think in pure water. That solid would ionize more. It would dissolve more. Okay, it would dissociate more than you would think. So the solubility of a solid would be greater in an inert salt solution rather than pure water because of this salt effect. It's fascinating. So there's a term we're going to introduce called the activity, right? Normally we just use molarities. Molarities is just assuming pure water and assuming the presence of these ions has no impact on it. Ho, incorrect. You have to account for the presence of these inert salt ions, or the salt effect, or interionic interactions, because it influences the equilibrium and shifts it to the right in these scenarios. So really, we should be doing all of our equilibrium expressions using activities, or the effective concentration taking into account the salt effect rather than molarity. So there's a small error in using molarities. Oh no, that's why a lot of classes don't deal with activities or the salt effect. It complicates things. So I just want to show you what this activity is and how it relates to molarity and how we can quantitatively convert from one to the other. So pretty much all of our stuff, we're going to be just ignoring the salt effect, except for a couple of our labs and maybe one problem on an exam. But for most of the time, we're going to be ignoring the salt effect. The more dilute the solution, the less of an effect it has. Obviously, the more ions you have, the more of an effect it's going to have. So let's take a look at that quantitatively a little bit. Alrighty, team. Let's take a look at this mysterious activity thing. All right, activity versus molarity. And ideally, you'll just never have to use activity, but I want to show you what it is and why equilibrium constants have no units. It's because, well, we'll find out in a moment. I don't want to ruin it. Here we go. Simple little equation I'll provide you. The activity or effective concentration of a species in an equilibrium expression, right? Usually on the right-hand side for weak acid, weak bases, and solid equilibrium, is equal to the molarity. Remember, these little brackets represent the molarity, and we'll just use some generic species X. So the activity of species X will equal to the molarity, what we call the normal concentration. This is the effective concentration, times some correction factor, all right, that accounts for the presence of these inert salt ions, or the salt effect. So that's called the activity coefficient of species X. So if we know the activity coefficient, right, for species X, we can just multiply it by the molarity like we normally do and get the effective concentration that accounts for the presence of those inert salt ions. So think of activity as an effective concentration or an adjusted molarity. That's probably the best way to think about that. Well, how do we get this activity coefficient? There's two ways, theoretically and experimentally. We're not going to do it theoretically. Not a very fun equation at all. So we're going to do it from experimental values and do some linear interpolations from a table I'll provide you on exams. So three things this is going to depend on. Hopefully this just makes qualitative sense to you. This is an interionic process. It's the partial attraction of these ions in the equilibrium expression to the presence of these other ions that are from the inert salt. Well, this is an electrostatic thing, right? So wouldn't it make sense that the higher the charge, the bigger the impact, right? So if I have a magnesium ion with a +2 charge versus a sodium ion with a +1 charge, don't you think things would be more attracted to a +2 charge than a +1 charge? Oh, big surprise! Or if I have an iron 3 ion with a +3 charge versus a lithium ion with a +1 charge, it's going to be a bigger factor if something has a +3 charge. So the charge of the ions has a dramatic effect on this salt effect, right? The stronger the attraction, the more it kind of obfuscates the particular ion, makes it harder for them to interact, harder to go back to the left, and causes more ionization and reduces the effective concentration, right? So the size of the ions has another one. The combination of 1 and 2 is really called the charge density we can think of, right? So the smaller the ion, the more impact, the closer it can get, the stronger those inner molecular forces lock into place, right? We're only going to worry about that if we do theoretical calculations. We're not going to have to worry about the size or the effective radius of that when we're doing the experimental effect that we do. Also, the number of ions. When it makes sense, the more ions there are, the more of a shell it forms, and the harder it is for them to combine, the lower the effective concentration, the more it shifts to the right. So let's take a look at how these impact that activity coefficient, because if we can figure these out, then we can figure the activity coefficient out, multiply it by the molarity, and get the activity. And we should be using activities in our equilibrium expressions. Okay, all right. These are going to be encompassed in a term called the ionic strength. Ionic strength of the solution, we'll call that I. So that ionic strength tells us the effect of the salt effect, right? The intensity of that salt effect, which deals with the number of those ions or concentration of those ions and the charges. So let me write up the equation for ionic strength, which I will provide for you, show you how to calculate it. All right, here's a quick way to calculate the ionic strength of a solution, right? So here's an equation that I'll provide you. So the ionic strength will be 1/2 the sum over all the ions present of its molarity, right? Which is kind of the number of ions in solution, times its charge squared. So it's highly dependent on the charge there. All these factors that impact the salt effect, right? So again, the brackets around it's the molarity, Z for species I, whatever, is the ion charge. So if we have 3 ions, we'll have 3 terms, 5 ions, 5 terms. Let's do an example, right? So what's the ionic strength of a 0.024 molar solution of potassium sulfate? So we got to identify what are the ions, what are their charges, and what are their concentrations. Then we plug them in and we get the ionic strength, and I'll show you how to take the ionic strength, figure out the activity coefficient. Once we have the activity coefficient, we can figure out the activity. Sweet. All right, so potassium sulfate is 100% soluble salt. So 1 mole of potassium sulfate gives us 2 moles of potassium ions and 1 mole of sulfate. So if I have a concentration of 0.024 molar for the original potassium sulfate solution, I would get twice that concentration. I get 2 moles of potassium ions for every 1 mole of this, right? So I'm going to get 2 times 0.024 or 0.048 molar. The sulfate's in a 1-to-1 mole ratio, so that will just be the same concentration, or 0.024. I know the charge on the sulfate's a -2. I know the charge on the potassium's a +1. I got everything I need to get the ionic strength. So let's take the ionic strength, which is 1/2 of, and let's start with the potassium here, and this will be the sulfate here. So I got 2 ions, so I got 2 terms. So I'm going to take the concentration of the potassium, which is 2 times 0.024 or 0.048 molar, times its charge of +1 squared, plus the concentration of the sulfate ion, 0.024, times its charge, -2 squared, which gives me a +4, right? So this becomes 0.048. That term from the sulfate becomes 0.096. I take half of that, add those together, right? Good to 3 decimal places. That's 0.144. So take half of 0.144. So the ionic strength is 0.072. That numerical value takes into account the impact of the salt effect. And then if you look in your general chemistry notes, there's a table. It's also a handout on my website that shows you how to get the activity coefficient from a given ionic strength. So this is kind of what it looks like. This is what I would give you on exams. All right, so it's got a bunch of different ions here. And then it has a value of activity coefficients, right, here based on the ionic strengths, right? So here on this top layer are the 0.001, 0.005, 0.01, 0.05, and 0.1. These are different activity coefficients, right, based on ionic strengths, okay? And then what we're going to do is find our ion. For example, you know, the lithium ion right here. At an ionic strength of 0.1, you take the lithium ion, go over. Its activity coefficient would be 0.80 for an ionic strength of 0.1. Crazy, huh? Let's take a different ion. Let's take the cobalt-2 ion right here. And let's say we had an ionic strength of 0.001. You cross-reference, so take the cobalt, go over to the column for the 0.001 ionic strength, and you would see it has an activity coefficient of 0.870. Pretty easy, and this is based on experimental data. We're not going to do the theoretical calculation. So we can use that table to get the activity coefficient from the ionic strengths, which we'll always have to calculate, but you'll be able to do that easily. You'll know the charge of the ions, you'll know the molarities of those ions. So let's look at how that impacts the activity. Right? And unfortunately for you guys, if you have an ionic strength that's in between these values, like this one, we have a 0.072 here, right? Oh, crud, it's not one of these columns, right? 0.072 is between 0.05 and 0.1. And we're like, oh no, so what if I wanted the permanganate ion? I would look across permanganate ion, so it's going to be a little bit smaller than 0.9, but a little bit bigger, a little smaller than 0.8, but a little bigger than 0.7. So it's between 0.8 and 0.76, which means we're going to have to do, yes, a linear interpolation, which I'm not going to do on the board here. You know how to do linear interpolations. Go find my handouts on that. You've done tons of those in lab. But to get, if you're not spot on with one of those values on the table, you'll have to do a linear interpolation to figure out what your activity coefficient is based on your ionic strength. That doesn't fall in between the values. And no, I'm not going to make you do a linear interpolation on an exam. Right? Or a quiz, they take too long. So let's bring back up that activity problem, and I'll show you how to solve for it. All right, let's see if we can do this. I simplified this a little bit because we're not going to do linear interpolations on exams, but we will in the lab, so prepare for that in the lab. So let's say we've got a phosphoric acid solution, and the phosphate ion concentration is 0.054 molar. We could have calculated that using an ice table. Let's say we did that. So we got 0.054 molar phosphoric acid, but we add in some sodium nitrate, enough sodium nitrate to give it an ionic strength of 0.05, which we could have calculated like we did on the last board, but to save time and space, let's just say it's an ionic strength of 0.05. All right, we want the activity. The activity of the phosphate ion will be the activity coefficient of the phosphate ion times the molarity of the phosphate ion. Well, I gave you the molarity, all right? We just want the effective concentration. So we need the activity coefficient, and that comes from the activity coefficient table. All right, so let's find, so an activity coefficient, so the ionic strength of 0.05 is right here at the top, right? And we need to find the phosphate ion, which is way down here. See the phosphate ion? So we're going to look across from the phosphate ion, to the second to the last column right here, which is the 0.05 ionic strength, and that gives us a value of 0.16. 0.16. So the activity coefficient is 0.16 from that table. Of course, if it was in between, we'd interpolate that. So now it should be pretty easy to calculate this. The activity will be the activity coefficient, 0.16. Now we're missing something, but I'm going to see if you can figure that out on your own. Times the molarity, which is 0.054 molar. Now, you tell me, activities are unitless. Remember when I introduced the activity, the equilibrium expression and the equilibrium constant. I said equilibrium constants have no units, and we kind of fudged it with molarities. Well, the reason is the activity coefficient, not the activity, the equilibrium constants we use in the back of the book are actually using activities, not molarities. And if activities have no units, equilibrium constants have no units. Hey, hey, hey. But if this is molarity and this has no units, what must the units be on the activity coefficient? Inverse molar. Haha. So those have units of inverse molarity. So let me get my calculator. We got 2 sig figs, 2 sig figs. So it's pretty easy to calculate once you have it. 0.16 times 0.054. I get, let's write this down. So the activity of the phosphate will be 0.0086. Good to 2 sig figs, 40, which does not round up. So in that scenario with that ionic strength, the actual effective concentration is 0.0086 versus 0.054. It dropped dramatically because phosphate's got a really high charge, all those kinds of things. So if we are using molarities, there's actually errors we're going to have in our equilibrium. Whoa, we should use activities. So let me do another board, kind of summarize everything, and we'll be good to go on this crazy new concept. All right, you ready to summarize the weirdness? There's the equation, pretty simple equation, right? Activity is equal to molarity adjusted by the activity coefficient. So think about this. As the ionic strength increases, the activity coefficient decreases, right? So as the ionic strength gets bigger and bigger and bigger, the activity coefficients get smaller and smaller and smaller, right? That accounts for the salt effect. So if the activity coefficient gets smaller, the activity must also get smaller, and so the activity coefficient gets further and further away or deviates further from the molarity, bigger salt effect. And the activity coefficient values range from, a little above 0 to 1, 0 to 1. So the activity is always lower than the molarity for dilute solutions and stuff. If we have ideal solutions, we just ignore this whole thing, right? But sometimes it doesn't happen. So these values range from 0 to 1, and they're just an adjustment factor. Let's take the molarity, adjust it for the salt effect, and we get the activity, right? So it's going to be almost like a percentage of it. They range from 0 to 1, so a neutral species wouldn't be impacted by the salt effect, so it has an activity coefficient of 1. If this equals to 1, then the activity and the molarity are the same. Hey, true for neutral species. So let's look at, there's 2 ways we can set up the equilibrium expression now. Let's take it for that weak acid we started with, hydrofluoric acid ionizing. We set up the equilibrium expression, so it's the equilibrium constant is the fluoride ion molarity times the hydronium ion molarity divided by the HF molarity, right? That's what we've been doing so far. But now what we really should be using is activities. So the equilibrium expression should be the equilibrium constant, the Ka, is the activity of the fluoride ion, the effective concentration, or adjusted molarity, times the activity of the hydronium divided by the activity of HF, which that'd be 1. It's a neutral species. How do you designate these 2 terms? We're going to use a special symbol for these, right? If we use molarities, we call that the concentration-based equilibrium constant. That's what the C is for. So we call it, anytime you see a superscript C, that means we use molarities, which is not the accurate one. If we use activities, we use T for thermodynamic. So this is the thermodynamic-based one. So thermodynamic-based equilibrium constant. Hey! Those are the values listed in the appendix. These are in the appendix or on the tables. So all those values on the KB tables, the KSP tables, KA tables, those are thermodynamic-based equilibrium constants. These are independent of the salt effect. They take into account the presence of these other ions. Concentration-based ones don't. So you'll see in lab that if you're measuring these in lab, they're going to differ from what you see in the back of the book, because the back of the book accounts for the salt effect. So it's independent of it. Pretty cool. If you use molarities, those K values can actually change as more ions are included into the system. Pretty nuts, right? Keep this in mind when we do some labs. Not very heavy in lecture, but we're going to do a lot of this in lab and apply it. Rock and roll, gang. Crazy stuff, activities.